These muscle fibers all have different sized neuron diameters which control the speed and force of the muscle contraction. Slow oxidative muscle fibers have a small neuron diameter, meaning that they have a slow and less powerful muscle contraction. In comparison, your fast glycolytic muscle fibers have a high neuron diameter, allowing them to produce a higher force at a higher contraction rate. Lastly, your fast oxidative glycolytic muscle fibers have a medium-sized neuron diameter, which allows them to produce both fast and slow muscle contractions with little or lots of power. But we say that these muscle fibers have medium power and medium speed of contraction. Slow oxidative muscle fibers work aerobically because of this. These muscles have a high fatigue resistance as they tire when the amount of oxygen taken to the muscles is restricted. There is generally a consistent supply of oxygen to the muscles, allowing them to function at a high quality for a long amount of time. Fast glycolytic muscle fibers work anaerobically, meaning that they have a very low fatigue resistance. As they do not use oxygen, the muscles cannot respire, meaning that they can work at a high intensity for a short amount of time, although it builds up lactic acid which can cause the muscles to fatigue. Fast oxidative glycolytic muscle fibers work both aerobically and anaerobically, meaning that they will have a medium fatigue resistance as they have a constant supply of oxygen but can also build up lactic acid. Lastly, your muscle fibers contain different amounts of myosin, ATPase. Your slow oxidative muscle fibers contain little amounts of myosin, as the more myosin you have, the more powerful the contraction is. Therefore, slow oxidative muscle fibers have little amounts of myosin, as the contraction with these muscle fibers aren't powerful. This means that the fast glycolytic muscle fibers will have large amounts of myosin, as their contraction is more powerful, and fast oxidative glycolytic muscle fibers will have a medium amount of myosin, as it can contract both powerfully and not as powerfully. The first type of muscle fiber to be recruited are the slow oxidative muscle fibers due to their high fatigue resistance, and then your fast oxidative glycolytic, and lastly your fast glycolytic muscle fibers. This is because your fast glycolytic won't be able to contract for a long period of time if needed to. However, your slow oxidative would be more able to. You are unable to change which type of muscle fibers you have, although if you have fast oxidative glycolytic muscle fibers, you can specialize your training to focus on building up fast or slow twitch within them for specific sports you want. So from what has been said earlier in the video, we can conclude that an endurance athlete like a marathon runner is more likely to have a high percentage of slow oxidative muscle fibers. A power athlete like a 100-meter sprinter, a thrower or a jumper are more likely to have fast glycolytic muscle fibers. And lastly, a games player like a footballer or a basketball player are more likely to have fast oxidative glycolytic muscle fibers. There are three types of muscle contraction, which are isometric, concentric, and eccentric. In isometric contraction, it is where the muscle contracts, but the muscle's length does not change. Iso means same and metric means length. Therefore, isometric muscle contraction is same length contraction. The muscular force exerted must equal the downwards force of gravity plus the weight of one if it's present. For example, when performing a bicep curl, the muscular force exerted by the biceps must be equal to the force of gravity and the force of weight in order for the arm to be at a right angle. In concentric contraction, the muscular force must be greater than the downwards force in order for the muscle to contract fully. When the muscle fully contracts, the muscle also shortens. So in the bicep curl, the force exerted by the biceps brachii must be greater than the downwards force of gravity and the weight being held. This brings the lower arm up past the 90-degree angle. Lastly, in eccentric contraction, your triceps brachii, which is the antagonist to your biceps brachii, does not contract because the lower arm has gravity forcing it down, so this means the muscular force of the biceps brachii has to lower so that it is slightly lower than the downwards force, allowing a controlled lowering of the arm. In eccentric contraction, lowering means lengthening of the contracting muscle. As you can see in this table, during the upward stage of a press-up, the triceps brachii are creating a concentric contraction. Now, during the downward stage, the triceps brachii are producing an eccentric contraction, meaning that the triceps brachii are lengthening. Lastly, during the midway stage, the triceps brachii are producing isometric contraction as the downwards force is equal to the muscular force being exerted by the muscles. A motor unit is the neuron and the muscle fibres it controls. The larger a motor unit is, the more force can be exerted. Fine control movements use motor units that contain very few muscle fibres per neuron, and gross movement use the motor units that have high muscle fibres to volume ratio. Muscle contractions all work under one law called the all or none law. This is where a motor unit uses all the muscle fibres in a muscle contraction or none of them. Lastly, the muscle tone is a constant low-force contraction in order to uphold a good posture. Your body changes with which motor units create the contraction so they don't fatigue and have time to respire. This can be seen in this picture. Your brain recruits which motor units will create the contraction by sending out an impulse. The amount of motor units excited determines how forceful the contraction is. Therefore, the more force wanted means the more motor units are needed to be recruited. Lastly, the type of motor unit recruited can determine how much force is exerted. For example, a motor unit containing fast glycolytic muscle fibres will contract with a greater force than a motor unit containing slow oxidative muscle fibres. These two graphs show a low-frequency contraction and a high-frequency contraction. These graphs show us that the impulses are sent at a constant rate, the contraction will be consistent. This is known as tetanic contraction, whereas if the impulses are sent at low frequency, the contraction will rise and then drop, and then rise a little lower, and then contract again, etc., etc., until the impulses stop. There are three phases to a muscle contraction. Firstly, you have the latent period, which is where the contraction starts as a stimulus containing action potential. The stimulus is transported through the body via the nervous system using neurons until it reaches the sarcoplasmic reticulum. This then releases calcium, which binds to troponin and reveals an actin binding site. The second stage of contraction is known as the contraction phase. This is the development of tension in the muscles because of the cross bridge formed between the actin binding site and the myosin heads. Lastly, you have the relaxation phase, which is where the previous tension in the muscle decreases due to calcium no longer being released, causing the actin binding site to be covered by the troponin. For example, when someone is thrown a football, they decide they want to kick it. Impulses will be sent out by the brain to the target muscles. The impulses cause calcium to be released, which means that the cross bridge can be formed so a contraction is made. Once the ball has been kicked, the impulse stops, which causes calcium to no longer be released, meaning that a cross bridge cannot be formed, therefore the muscle relaxes. This picture shows a nerve, and the nerve ending is where you will find a neuromuscular junction. A neuromuscular junction is the nerve ending. It is when the vesicle containing ACH is produced and diffuses over a synapse into the muscle fibre. More will be explained about this on the next slide. The sliding filament theory is when your eyes detect a stimulus. A ball is this example. An impulse is sent from the brain down a neuron, jumping over the myelin sheath, landing on the node of Ranvier, each time by saltatory conduction. The moving impulse is called depolarization, and an impulse is an electrochemical signal. The impulse reaches the neurovascular junction, which contains vesicles, which contain a neurotransmitter called ACH. The ACH then diffuses over the presynapse membrane, through the synapse, and out of the postsynaptic membrane. After the diffusion, if enough ACH makes it across, then the impulse will go down both directions of the muscle fibre. Then the impulse is sent along the T-tubule into the sarcoplasmic reticulum, which stores calcium. This triggers the release of calcium, which then binds to troponin inside a sarcomere, forcing it and the tropomyosin to move and show the actin binding site. At this point, the myosin heads have bonded with ATP, causing them to become highly energized. The energized myosin heads bind with the actin binding site to create cross-bridge. Now, a power stroke forces the actin along, making a contraction. The myosin head now bonds with ATP, releasing ADP and phosphate, whilst releasing the actin. The myosin is now energized again, as it has bonded with ATP, meaning that it power strokes the next actin along, making the contraction harder. When the brain wants the contraction to stop, the impulses will be stopped, which have been sent continuously throughout this process, meaning that the calcium is no longer released, and therefore the troponin and tropomyosin are replaced to cover the actin binding site, allowing the muscle to relax.